All right, today we're going to be looking at critical points. So if you recall last semester in advanced functions when we were graphing these rational functions, when it came time for us to actually draw this, this little curve part, we didn't know exactly where the point would go, or this bump here, we didn't know exactly how high that bump is. So we just had to guess it. Now that we know something about calculus, we know that these points are little local maximums and local minimums. And we've learned already that if we take the derivative and set it equal to 0, we'll be able to find these points. Remember, the tangents of these curves are all going to come, and then the tangent's going to be straight across like that. And when it's equal, so when that slope is 0, we'll know that there's a critical point. So we're going to use the calculus to make these graphs a little bit more accurate. And that's what today's about, finding critical points. So the critical points are local maximums and local minimums. We know we can find them by doing the first derivative test, taking the first derivative of these functions. So we're going to do an example on a polynomial function right now. Most of the examples we're going to do today are polynomials just because the equations will be a little bit easier to calculate as we get used to the process. But then tomorrow we'll be actually using the first derivative test on rational functions, more complicated situations. For this polynomial function, you can see that there are some critical points. You can just see them. We know that there's one there. It's a local minimum. It locally in that area is the lowest point. And then we've got two maximums here and here. So what we'll want to do is to find those, we know that the slope of the tangent is going to be 0 at here and here and here. So the first part is to find the critical points by setting your derivative equal to 0. And we'll be able to identify where these critical points are. Second, though, we might want to figure out, is this a local max or a local minimum? So if we didn't know what the shape of the graph is, we just have these points, it would be difficult to tell if they're maximums or minimums. Um, so we'll want to confirm that by using the first derivatives as well, the slopes of the tangents. So imagine the pencil test on the graph right here. So we know the graph's increasing, so the slopes of the tangents are all going to be positive. Imagine a pencil with the tangents going along here. These are all positive up until we get to this point here where the slope is 0. And then afterwards, the derivatives are all negative. The slopes are all negative. So if the graph goes from, if the derivatives, the tangents, go from positive to negative, that must mean that you have a local max. So if the derivatives change from positive to negative, you know you've got a local max. Similarly, the graph is going down here, so the slopes of the tangents would all be negative, 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 until you get to here where it's 0, and then it switches and the slopes become positive. So if the tangents go from negative to positive, then we know that we have a local minimum. And in this example, we've got another maximum. So before it's positive, after it's negative, so we go from positive to negative, means that that must be a local max. So this is the testing we'll have to do on functions when we don't know what the shape is, or maybe we only have one point and it's hard to tell if it's a local max or local minimum. We'll be doing this first derivative test. So we'll do it with this first example. Now, in this example, you'll notice it's a quadratic. You probably already have an idea of what this shape is, what this picture is, seeing that it's a negative x squared. But we're going to pretend we don't know whether it's a local max or a local min. And we're going to go through the process to be able to figure out how we'll prove that it's a local max or a local min. So just ignore these orange things for a second. We're going to go off and try and figure out the critical points. So first we'll have to differentiate it, set it equal to 0. So the derivative of 4x is just 4. And the derivative of x squared is 2x. So of course the derivative is 4 minus 2x. And if we're finding local maxes or mins or critical points, we set it equal to 0. Solve for x, so that 2x can come across, divide both sides by 2, we get x equals 2. So we know that at x equals 2, they must be a critical point. What we want to find is the y value as well. So to get the y value, of course, we take that x equals 2 and sub it back into the original, not into the derivative, into the original. So by plugging that in, f equals f at 2, so instead of x, it's 2, so 4 times 2 is 8, 2 squared is 4, 8 minus 4 is 4. So we know that there's a critical point at 2, 4. What we haven't proven yet mathematically is whether this is a maximum or a minimum. We just know that we've got our graph here and a point And this point is sitting right out here. We don't know if it's a max or a min. We probably have a guess of that it's a max or a min, but right now we don't know if it's a max or a min. So how are we going to do that? Well, we want to go off and figure out if what the slopes of the tangents are doing and what's happening at all the points before and after. So again, we're going to use the derivative. So what we need to do is set up this chart. This chart's going to help us organize um, what we're discovering about the derivatives and therefore what the function itself is doing. So you're going to see a chart like this where you're going to have your intervals up here. You're going to investigate what the derivative's doing, and by knowing what the derivative's doing, you'll know what your actual function's doing. So we're interested at when x equals 2. That's our point. We know already that the slope of the tangent here is 0. We've proven it right here. Okay, so we know the slope of the tangent's here. What we don't know is if the graph is coming like this, so what are the derivatives doing before, the tangents doing before or after. So these are all the intervals before and after. So we have to investigate the derivatives before. So if we're going to look before, we're going to look at x values that are less than less than 2. So over here, less than 2. And then what the derivatives are going to do afterwards, which would be x greater than 2. So is it going up or down? So we got to investigate the derivatives. So here's the derivative. So we're curious about figuring out what the derivative values are going to be. Are they going to be positive or negative? Now it's best to make sure that it's in factored form. This will be a little bit easier to figure out whether the derivatives are going to be positive or negative. So if it's in factored form here, the common factor is 2, so you can put it out here. So we're going to plug values for x that are in this interval and find out if the result is going to be negative or positive. Just like we were doing before, we don't actually care about the number, we just care if it's going to be positive or negative. So in this instance, for x equals is less than 2, we can pick a number like 1 or anything less than 2. We're going to pick 1. So the 2 part's going to stay positive, but when you put in 2 minus 1, that's also going to be positive. So that means you're going to have a positive times a positive, which is positive. So this tells me that the derivative, the slopes of the tangents, all the tangents, remember these tell me all the slopes of the tangents. When x is less than 2, all the slopes of the tangents must be positive. That means the graph is going up. So we have some proof now that the graph is going up. I'll suspect that it's going down, but we need to prove it afterwards. So x is greater than 2. So what would happen if we put in a number bigger than 2 into the derivative? So we'll pick a number like 3. Again, the 2 is going to stay positive, but 2 minus 3 is going to result in a negative here. So this is going to be a positive times a negative, which is negative. So that suggests that the graphs afterwards, all the tangents are negative, which means the graph must be going down. And therefore, if the graph is going up, and then going to 0, and then going down, that means that you must have a local maximum. And now we've proven and convinced ourselves that this critical point is actually a maximum, and we know the graph goes like this. And what's special now and different than what we had before is we didn't know where that point was. Remember, we were just guessing where the sort of hump would be, but now we actually know and have proven mathematically that this is the highest point and a critical point for this graph.